Hi everyone, it's Dr. Antonelli, and we are going to discuss Chapter 4 in our Intro to Psychology class in this recording. And we're talking about sensation and perception tonight. Basically, what you need to keep in mind as a quick overview of this entire chapter is that when we are dealing with the senses, we are dealing with vision or sight, hearing, which are sounds, touch, taste, and smell. And we're going to look at each of those individually and how they create different sensations, which then will affect our perception of what we are experiencing. Okay, and then our behavior obviously connects to what we are experiencing. All right, so there are a few modules or sections of this chapter. The first one is all about vision. It gets a little bit tedious with some of the structures of the eye, as well as how things and light enters the eye and where it goes from there, important parts and structures in the eye, and how all of these things kind of impact our vision. Okay, so let's start off with kind of a basic idea of what vision is. Vision is really the simplest way to put it is kind of a detection of light. It occurs when light actually enters your eye, and these light rays strike what we call the retina, which is located in the back of your eye. And in doing that, it causes some cells to send messages then to the brain where we perceive the object that we're looking at. And we kind of say, okay, that's this, for example. Okay. It sends, remember, to the part of the brain that it sends these messages to is known as the occipital lobe. You guys did the occipital lobe and the other lobes as one of your discussion questions last week. And it's important to remember that when we're talking about perception, we're talking about how our brain basically translates a stimulus, something that enters our eye, like light, into something different. And it really, this translation occurs and will depend on experiences we've had and kind of things we already know. And that's why perception varies from person to person. Okay, so again, keeping in mind that vision is light entering your eye. We do not send sight rays out of our eyes. When we talk about vision, it's only about the entering of our eyes of light. Okay, how do we detect light? The way we know we're detecting light is we feel the sensation of a stimulus. A stimulus is something that comes from around us and then affects us in some way. Okay, and then we have these thing called receptors, and a good way to remember the word receptors is it sounds like the word receive. Receptors are things that are located in our eyes and our ears and basically in all of our sensory organs. And they're kind of a group of specialized cells that take what we take in from the environment, and then, you know, they kind of process what we take in, and they convert these things we take in into a signal that gets sent then to the nervous system that allows us to perceive something that we're seeing or hearing or feeling or tasting or smelling. Okay. Another important piece to detecting light has to do with the electromagnetic spectrum. Think of a spectrum as a range of something. So the word continuum and range go together. And it's basically where all parts of energy kind of come together. So more specifically to light is a part of this spectrum, and it contains many different kind of wavelengths. Wavelengths could be things like infrared, ultraviolet wavelengths, x-rays. Those are a few examples of wavelengths that are part of this spectrum. Some of these we see, some of these wavelengths we can actually see, and some we actually don't see. Okay, so it's kind of interesting to think about wavelengths in that way. Okay, this next slide really takes us into the nitty gritty of the parts of the eye, and it really does give us a nice kind of overview using, kind of background information on, lens gets its name from the Latin word lens, and it means lentil. If any of you have ever had lentil soup, Lentil almost has like a shape of like a bean, I guess you can think of it. And if you look clearly right here, this roundish oval kind of shaped piece of or structure in the eye is known as the lens, and it almost looks like a lentil if you've ever eaten lentils, like in a lentil soup. All right, it kind of goes with the shape. All right, so it's important to kind of make that connection for yourself. There are so many parts to the eye, so let's take a look quickly at each one. Let's take a look first at the pupil. The pupil is like a shade. Think of it, it's right here in front of the lens. Think of a shade in your room. You open it and close it. You adjust that shade up or down to let light in and out. Then we have something called the iris, which is the colored area right here above the pupil. The colored area, the iris is really your eye color. So most people have either brown or blue or green eyes. Okay. Then we have the retina, which is down here, and it kind of expands all the way around. Okay. The retina is kind of the back surface of the eyeball. Okay. So this whole section here is the eyeball, and the retina kind of is the back piece of that. Okay. Then we have the cornea, which is back here in the front. Okay. The cornea and the lens, they kind of work together. They're almost like partners, the cornea and the lens. So think of them on this diagram. They're both kind of shown in blue. Those two areas work together to help focus light on the retina in the back. So the light enters, and the cornea and the lens work together right here to focus that light and get it into the retina. Okay. Then we have what's called the fovea, which is here in the back. It's this little section that's here in the back. It's really the central part of the retina, okay, because this whole back area is the retina. And it's the central part where there are receptors or cells that are going to receive the light that comes in and will help us to adapt what we're looking at, okay? And remember what receptors are again. They are things that help us to receive those messages of light that are coming into our eye. There are two kinds of receptors: rods, which kind of help with the focus of dim light, and cones, rods and cones, and those are listed up here. And cones, which have to do with color. So a good way to remember cones is both words start with C, cones and color. And cones are receptors that deal with the color that you see as well as any details you see in bright light. Okay. Then another piece you need to remember that's not on this diagram specifically are things called bipolar cells or neurons. The neurons receive messages from the receptors. The receptors are the rods and the cones that we just talked about. So they receive these messages and then they send out a message to our brain to say, hey, that is this color, or that is an object that looks like this, and we interpret it from our brain based on our experience. Okay, so the pathway through the eye has to do with starting, the light comes in, it goes into the pupil, it goes into this section in the center and goes straight through and to the retina. Okay, so again, you could take a look in the textbook. It gives a kind of more description, but that's the general idea of how things work. All right. Color vision, we have to ask ourselves the question of, well, how do we see in color? Okay, cones have a big piece to this. Remember, cones see, color see. Okay, so let's talk about the wavelengths and what actually occurs. All right, there's a lot of words on this slide, but I'm going to simplify it for you. When we look at the first bullet point here, this talks about how a wavelength of light will enter the eye, and it will kind of match up to a cone somewhere where the rods and cones are that it best fits with. Some wavelengths fit better with certain cones than others, okay? Then you have to remember that in this visual path, okay, the length, how long the wavelength actually is, and there's three kinds of wavelengths: short, medium, and long. These three wavelengths will kind of help to decide how it will be coded after it enters the eye, meaning what will the receptors do with it after it enters the eye. It depends on the wavelength, whether it's short, medium, or long. That would be the decision maker as to what the eye does with that information, that light that comes in. Okay, and then the wavelength info, that after it kind of codes it based on short, medium, and long, that wavelength info is then sent to the brain to decide what colors we will see. Okay, so that's the description of what these 3 bullet points here are on this slide. Okay, there are 3 theories that actually help explain color vision. The first one is called the trichromatic theory. You might want to circle or in your notes highlight the tri part of trichromatic, because tri stands for 3. All right. So it's important to remember that, because we're going to talk about how there's 3 things involved here. It's called the Young-Helmholtz theory, also known as the trichromatic theory. And it basically says that color vision depends on how 3 types of cones respond to the light that hits them. Okay, so each cone is going to react to a wavelength differently, which impacts what color we eventually will see. Okay, so for example, one type of color really is most sensitive to shorter wavelengths, which generally then we see as blue. Another type of color is most sensitive to medium wavelengths, and that's what we often see as green, and then the longer wavelengths is what we often see as red. Basically, what this means is how the cones link up to the wavelengths determines or impacts what color we will see. Okay, so if you think about, let's say you have 3 people on one side, let's say in a room, 3 people standing on one side, 3 people standing on another. Person number 1 on the left side may react best, let's say, with person number 3 on the right side. And person number 2 on the left side may react best with person number 1 on the right side. And then person number 3 on the left side may react best with person number 2 on the right side. It's the same principle of these colors and how they react the best as wavelengths to help us process which color we're going to see. Okay. The second theory to help explain color vision is called the opponent process theory. The opponent process theory basically says that we're going to perceive color in terms of opposites. Red versus green, yellow versus blue, and white versus black. For example, if we stare at something red for a period of time and then we look away, we will often see a green after image. Okay? Another example, if we stare at something yellow for a little while and then we look away, we often see a blue after image. Okay? That's the opposite thing that it's talking about in the definition. When we talk about negative after images, okay, I need you to think of something. Cells in the nervous system, okay, they become tired of seeing the one color that we focused on. So that's why then when we look away, we often see the opposite color as our response. And a good example is if you were to stare at the McDonald's logo, but the McDonald's logo is blue, the one you're staring at on the paper. If you stare at that blue McDonald's logo for a while, then you look away. When you turn back and look at a solid white piece of paper, let's say, you're actually going to see it in yellow, because your cells that were seeing the blue became really tired of focusing on that one color. And so when you turned away, you then saw the opposite. Okay? All right. The third theory, moving on, that helps explain color vision is called the Retinex theory. Okay? The Retinex theory has to do with a few kinds of concepts. The first one is about brightness. And the question to ask is, how does the brightness of an object change when looking at things around it. So, or does it change or does it stay constant? That's what this is really referring to. So, when we're looking at something, whether on a piece of paper or in our environment, how bright it is apparently is based on how we see things around it. Okay. Um, and the color constancy concept is, does the brightness kind of change based on the objects around it, or does it kind of stay nearly the same? That's kind of the idea of these two concepts. So the Retinex theory says that the cerebral cortex, now remember the cerebral cortex, you did a whole discussion question on the parts of the cerebral cortex, okay? That's the area of the brain that analyzes light, which impacts our perception of what color we are seeing. So the Retinex theory says that the cerebral cortex kind of takes in the pattern of light and analyzes it and compares it, um, and then kind of comes up with its own color perception. Okay, so the retina, there's the theory Retinex. Okay, has a role in this because the light comes in. It focuses on different parts of the retina, which I showed you in the eye photo, the structure earlier. And depending on where the light comes out of the retina is how we will then, how the cortex, the cerebral cortex, will then kind of analyze and decide what color is going to come out of that. Okay. So those are three theories of color vision. We also have these ideas of color vision deficiency. So the idea of color blindness, where someone doesn't see any color, is very rare. That's color blindness is where we can't distinguish color at all. Extremely rare for individuals to have this. Okay. However, certain people have difficulty distinguishing reds from greens, those particular two colors, and there are genetic factors for that. Okay. Without getting too heavy into biology, if you remember, this coloring of red and green exists as a recessive gene on the X chromosome, genetics. So men have only one X chromosome. So they only need to have one gene to have this red-green deficiency. Therefore, this red-green deficiency is more common in men. Women have two X chromosomes, so they would need two genes to get this red-green deficiency. That's a lot less common. So it's less common for women to have the deficiency because you have to have two genes in order to get the deficiency because it's on the X chromosome. Okay, and women have two of those X chromosomes. So there's a better shot at men getting it because you only need to have one of them, and men only have one X chromosome. Okay, think of a lottery ticket just as a comparison. If you're picking 8 numbers, if you picking one of those 8 numbers correctly to match what comes out in the lottery ticket, you probably have a better chance than picking 2 correct numbers out of the 8. That's what this refers to when kind of comparing the males or the men to the women when it comes to the red green color blindness. Okay, that particular piece. All right. So this was the first sense that we talked about is vision. Now we're going to move on to the second part of the one of the parts of the chapters that have to do with hearing, touch, pain, taste, and smell. All right. So let's talk about hearing for a second. A lot of hearing has to do with sensations, also known as vibrations. Okay. Do you ever play music really loud and you put your hand, let's say, on the where the music's coming out of the speaker, let's say, and you could feel a vibration? That's what we're talking about here when it comes to hearing, is these sensations or vibrations that we feel and perceptions of what we're hearing. Okay. So let's talk about some terminology. Sound waves, straight definition, are vibrations of air, water, or other things. Okay. Hertz, and for short it's known as Hz. These are cycles per second, meaning how many vibrations per second are we feeling? It's the frequency of a sound wave. Okay, so think about a sound wave and how often a sound wave occurs. Okay, then we have something called pitch, and pitch is a high frequency sound wave, which often creates a really high pitched shrill sound. We can also have a low frequency sound wave as part of pitch, and that's just a lower sound level. Okay. Another word that goes with pitch are called octaves. If anyone plays a musical instrument, especially piano, but all musical instruments have octaves. A piano has octaves from low to high. Okay. And that's what we mean by pitch. Okay. Then we have the idea of loudness, which is how intense or how strong are the sound waves. That would be loudness. Then we have something called timbre. Timbre has to do with, and you might want to put a circle here on the T for timbre and a T for tone. Timbre has to do with the tone complexity, and let me explain what that means. Think of ingredients in a recipe if you are baking something. Beyond your basic ingredients of egg, let's say sugar and water, okay, is there any other ingredients that make that recipe more complex? That's what timbre refers to. Okay, it's take a basic sound and then add more complexity to it. How complex is the sound? That's what timbre refers to. And then we have the cochlea, is how you say that. These are fluid-filled canals, and we're going to show the diagram of the ear in a minute. They look like a snail, meaning they're kind of raveled up, and these areas contain the receptors for hearing. Like we talked about rods and cones being the receptors of vision. Well, we have the cochlea as the receptors, the fluid-filled canals as the receptors for hearing. They tend to, these canals, convert anything that's weak as a sound wave into a more intense one. Okay, so let's kind of take a look at the diagram as it's again, lots of parts, but pretty well diagrammed here. The top is what you is inside the ear, and the bottom part of this diagram is the cochlea unraveled. Like, see how it looks like a snail? It's all raveled up. If you unravel that and make it go across like this, that's just so you could see what's going on and how the wavelengths move, you know, from one spot to another and back and forth. Okay, so just so you know, there are a few things that go on here. The sound waves go into our ear and they vibrate the eardrum, which is this area right here. Okay, then these three tiny bones that are called the hammer, the anvil, and the stirrup. These three tiny bones then kind of take that vibration in the eardrum, okay, and they convert it into a vibration in the fluid-filled cochlea, which is over here in this area right here, okay? Then these vibrations displace, you got to go down here to see them, these little hair cells that are all along the coiled up cochlea. Here it's uncoiled to show you. But there are these tiny little hair cells along here that are named, that is where the vibrations travel, okay? And then these little hair cells connect to neurons and the auditory nerves, which then carry the message to the brain. And remember, in this area, brain area, we're talking about the temporal lobe, so that the brain can then interpret what we are hearing. Okay, so again, it's pretty well spelled out, and it gives you a good idea of when sounds go in, how they're actually converted into something we hear. Okay, let's talk about pitch perception. Now, remember what pitch was. These were octaves from low to high. How we hear something as low or high is kind of guided by these three principles that are here. The first principle is called the frequency principle. And basically what that's saying is a sound wave goes through the fluid of the cochlea and it vibrates all the hair cells. Every little hair cell that's in there has a vibration that happens to it, okay? So there's a lot going on in there, okay? So each hair cell is doing some sort of impulse, sending messages to the brain, and working together in synchrony, okay, with the sound waves. So picture two instruments when you're think about two people playing two different instruments. They're both playing at the same time, but they're playing in a synchronous way with each other, and they work together, okay. And this is where all the each hair cell will send an impulse, you know, to the brain. Okay. Then we have the second principle of pitch, and it's the volley principle. Think about uh, volleys as groups. Okay. So instead of each individual hair um, kind of sending out these impulses, groups of them get together. And the reason is because so much sound is coming in that each individual hair is unable to kind of keep up with the pace of the vibrations coming in. Okay. So they almost have to work together in groups to respond to these vibrations because there's just too many coming in. It overwhelms each individual little hair cell. All right. Then we have the place principle, which is kind of the highest frequency or pitch because it vibrates these hair cells, and it takes place. So it's where the sounds vibrate the hair cells. That's why it's called place. All right. It kind of vibrates them near what we call the stirrup end. Um, and it vibrates them further along down on the membrane. Okay, so if you go back to your diagram, okay, and we look at the uncoiled cochlea, it's the place principle is further along down, and here it's in the stirrup, it says, near the stirrup end, is where we have the highest frequency, okay? And then as it gets further along, it almost lessens in frequency. So if you think about it, the vibrations are really strong at the beginning, and then they kind of get weaker as we go along the uncoiled cochlea here, as you see it. Um, and what that means is we have the highest frequency in the early stages of the vibrations going in, and then as it gets further down, they weaken a little bit. And so those are lower frequency sounds. All right. So that kind of helps to think of it that way. Okay. As something, think of when something, a ball gets thrown, it's usually faster when where it first gets thrown versus when it gets to the end of where it's being thrown. Then it's going actually a little slower if you think about it that way. Okay. When we talk about localizing sounds, you know, it's a couple things to remember. You're trying to figure out where is it coming from. So when you're standing there and you hear something and you're trying to identify where's that sound coming from? Do you ever stand in a room and say, hey, I hear something, but I don't know where it's coming from? That's what we're talking about here, okay? When you hear something, the action takes place actually inside your ear in all those structures and processes we just talked about, but then you experience the sound outside of your ear, okay? And we kind of only can do this usually in a relative or approximate way. So the first way we can do this is by kind of saying, hey, when am I hearing it and how loud is it? Okay, in both my ears. And if something is getting louder as you're standing there, it should imply to you that it's actually coming closer. And if the pitch or the higher sounding sound is coming closer as well, then you know it's all getting closer. All right. But those kinds of figuring out where it is, and how close it is to you, it's kind of like a guess. You can't really identify how far a sound is. You're only guessing at that point. Okay. And the way we can actually measure it more definitively is by listening to an echo. So, we first hear the sound, and then if it reflects off a wall and comes back to us, we hear it again. And that is the only way we can really identify, in a more definite way and measure it, kind of the distance of where it is in relationship to us, is when we hear echoes. That's really the only way. Okay? So it's kind of important to to think of that way. Okay, so how far away is a sound from us? We really can't measure it unless there's any sort of reverberations or echoes. All right. When we talk about the vestibular sense, um, these are, again, still having to do with sensations that come from what we call vestibules in the inner ear that are on each side of your head. So, what you need to do is think about being on a roller coaster with your eyes closed. Okay. This system, called the vestibular sense, will detect how your head is moving and where it's oriented in relationship to the rest of your body. Okay. This particular sense plays a role in how straight you stand and how balanced you are. Okay. It also is one of the key areas that's responsible for motion sickness. And I don't know if any of you, when you're on a roller coaster, experience motion sickness, but this is the area that, kind of deals with that. And then it also enables you to keep your, eyes fixated on something while your head moves. A lot of times, if you're on, let's say, a rocking kind of boat, you're on the ocean in a boat that's rocking. If you keep your eyes kind of fixed on, let's say, the horizon or something that's a solid target, then is your head moving or not moving? If your head is moving because the boat is rocking and you're able to keep a focus on one item or the horizon or the sun or something, then, that helps, is moved along by this sense. It helps you with this. Okay. So there's a great activity that the book kind of describes. If you have a book in front of you and you move the book kind of back and forth, but you keep your head steady. Okay. Try to read it at that point. Can you actually read it? If you have a book, you keep your head steady, but you move the book back and forth. Is that easy to read or hard to read? But instead, now keep your book steady and move your head back and forth. Is that easier to read or hard to read? Actually, the second one, where you keep the book steady but you move your head, that's actually easier to read because the vestibular sense keeps your eyes fixed in one location. Okay. And that's really kind of an interesting thing. Okay. So if you take a look in the book, we might do that activity actually in class so that we all get a sense of what we mean by vestibular. Okay. The next area has to do with a group of things called the cutaneous senses. When we talk about the cutaneous senses, we're talking about the senses of the skin. Okay, so skin senses, a lot of S words here. And then you might want to also remember another S word called the somatosensory or body sensory kind of senses. All of these things have to do with mainly touch, but then there are a couple of other things that are related to it. So we're talking about touch really when we talk about the cutaneous senses. Okay, some examples are warmth, pain, which hold that thought on pain because we're going to expand that over the next couple of slides. Itch, vibration, and tickle. Did you ever realize that you can't really tickle yourself? I don't know if anyone's ever realized that. Does anyone know why they can't tickle themselves? Well, because your brain builds up anticipation. And if you know you're about to try to tickle yourself, your brain has already been cued in that this is going to happen. And that's why you can't tickle yourself. There needs to be an element of surprise when it comes to a tickle. Okay. So, again, just as with hearing and vision, there are items or things called receptors that actually assist with how we feel things, okay, to the touch. All right, let's talk about pain. Pain is a cutaneous sense, okay? Um, the experience of pain is a combination of things. It's a combination of body sensation as well as emotional reaction, okay? And it depends on the different brain areas that are processing the experience of pain. So let's talk for a second about physical pain. Physical pain may be really intense at a certain moment, but then it's not lasting. So let's say you cut your finger. When you first cut it, it's obviously painful, but a day later, it's not really long-lasting pain, okay? Emotional pain tends to last longer in intensity versus physical pain. Okay, so there's a couple of ways to think of pain, all right? Let's talk about the gate theory of pain. The gate theory is that um, pain messages have to pass through this gate, okay? Um, and technically, the gate we presume, is in the spinal cord somewhere that can or may not block messages, okay? Um, so, other kinds of input that we actually do can close the gate and reduce the pain, let's say. And let me give you an example so you understand what this means. Let's say you injure yourself, like you bump your knee on something, the end of your bed as you get up in the middle of the night, right? You bump your knee. Sometimes if you go and rub like the areas surrounding the area that you bumped or knocked something into, it kind of sends a message to close the pain gates. So if you've ever like bumped into something or, hit your arm, your elbow, and then you start rubbing the area around it, that rubbing is a good thing because it's almost sending the message to say, hey, close that gate so that the pain, it doesn't get to be so bad. All right. There's a few ways to decrease pain. Let's look at each one. Um, Distraction. All right. It has been found that let's say someone has surgery, and after surgery, the individual gets put in a room with windows so they could see outside. The sunlight can get filtered in. This has been found to decrease pain, where people who are in that kind of a room after surgery often need less pain medication, and they often report feeling less pain. Okay. Another way to decrease pain is this idea of endorphins. Endorphins are these neurotransmitters, that should be a familiar word to you from one of our prior chapters. Neurotransmitters that actually kind of lessen the pain sensation. And we can increase our endorphins by pleasant experiences, things like exercise, things like music is a great endorphin as a way to weaken a pain sensation because it just gives us a positive, good feeling. Okay. And then we have something called capsaicin, which we rub onto the skin. It's an actual chemical that stimulates certain receptors that respond to painful heat. So it's kind of when you rub it on your skin, it provides this temporary burning. And you say, well, burning is bad, but again, it's a temporary kind of burning sensation that occurs. But then, as a result, the pain loses some of its sensitivity. The skin loses some of its pain sensitivity. So those are like those topical creams that you can put on that will kind of stimulate receptors, through this burning sensation to kind of have the skin lose the sensitivity it has to whatever pain is going on. Okay. Then we have something called phantom limbs. And here's after, let's say, a limb in an individual may have been amputated for whatever reason. Um, Sometimes these individuals have reported continuing sensations, okay, including pain, even though the limb is no longer there, if a leg is amputated or an arm is amputated, etc. So the part of the brain that processes the sensation from a limb also becomes inactive after there's an amputation, let's say of a hand, for example. But then the axons, which are the things that move the messages from another area, they strengthen or pick up these connections from the amputated area to the brain. For example, let's say from the face area. And then over time, these axons that are bringing these connections from the face area tend to start stimulating the hand area, even though the hand is no longer there. So it's almost like one path. When you have your hand and you have a connection between your hand and the brain, and then you have connections from other parts to your brain. If one part is amputated, kind of this connection, this pathway, joins up with another connection or pathway of a limb that still is there. Okay. And what happens is people continue to feel a sensation, including pain, in the area that was amputated. Okay. Because the pathway actually just kind of, went into the pathway of another limb. Okay. And that's why they're feeling the sensation, including pain sensation. Okay. Um, so we had touch as a cutaneous sense, and now we have taste. Taste is a chemical sense. Okay. Taste is part of a sensory system that kind of detects chemicals mainly on the tongue. We have these things called taste buds. I'm sure you've heard of them, but they're kind of folds that are on the surface of the tongue. You really can't see. They're not large folds, okay, microscopic folds on the surface of the tongue where the taste receptors are located, okay? In adults, the edge of the tongue is where most of the taste buds are. But in children, the taste receptors are more widely distributed over the entire surface area of the tongue. Okay, so if you're eating something and it's more toward the sides of your tongue, as an adult, you're going to get that taste to be more strong. Okay, whereas with children, it's distributed all over the tongue. So whatever they eat tends to um, tend to taste it no matter what part of the tongue it's touching. Okay, there are types of taste receptors. The four primary tastes that we have in Western culture are sweet, sour, salty, and bitter. Um, Bitter is an interesting one because there are many diverse chemicals that actually taste bitter, and they're very harmful in large amounts. So if you're someone who likes the bitter taste of certain, that is in certain foods, um, there's a lot of chemicals that make up that bitter taste, and actually, some of these are quite harmful if we have too much of them. So, bitter's an interesting one. All right. Then we have something called umami, and this was a Japanese word for the taste of MSG, often which you hear about in Chinese food. But MSG cannot be described by any of the above four tastes there. It cannot be described as sweet, sour, salty, or bitter. And that's why this other category or type was kind of created. Okay. Then we have smell. Smell is also a chemical sense, just like taste. Um, a bigger word for smell that we refer to a lot in this PowerPoint or in the chapter. They refer to it as olfaction. Olfaction is basically your sense of smell. And then again, we have these receptors. They're called olfactory receptors, and they're located in the rear of your nose, and that's where the detection of airborne molecules as you breathe in happens. Okay. Human beings have hundreds of these types of receptors. What's interesting is that rats and mice have about 1,000 or more. Okay, so rats and mice have more, a better sense of smell because they have more of these olfactory receptors than humans do. Okay, many odors produce what we call strong emotional responses. Okay, but the key is that your response or reaction to an odor really does depend on what you think it is. There's a whole section in the book that kind of describes what people actually are told they are smelling, and then they have different reactions. So at one time the description in the book says people are told this is cheese that they're smelling, a certain kind of cheese, a Parmesan cheese, and they're like, oh, that's a great smell. They have like a positive kind of response or reaction. Then they're told, oh no, wait, I made a mistake, that wasn't the Parmesan cheese, that was actually vomit. And so then the person has this real negative reaction, and then the person comes back and says, oh, wait, no, I made a mistake again. That wasn't vomit. That was the correct Parmesan cheese. And the person almost says, oh, okay, right. It smells really good to me. So the responses kind of are different, almost based on what they think the item is that they're smelling. Okay, it's an interesting kind of piece to this as well. So here's kind of a connection to behavioral responses that we've been talking about in our course so far, how everything kind of connects with behaviors. Okay. The rest of this piece of smell has to do with the important functions in most non-human mammals, okay, that olfaction kind of serves as a function for. What that means is, um, for animals, let's say, they use smells to kind of recognize one another, and they use it especially during mating season. Certain animals give off a smell that will either imply to the other animal that the animal is, willing to be part of the mating process or not. Okay. And then we talk about it as humans as well, in that it's very important to our social behavior than we actually want to admit. What that means, they give a couple of examples in the book, that if we smell a woman who is sweaty, that smell to a man is usually good. However, the opposite, okay, meaning a sweaty man smelled by a woman, is usually not good. Okay. Um, in addition, people in general, most people don't like the smell of their own relatives. That's kind of an interesting little tidbit that the book puts out there that I thought was interesting to share. Okay. Um, there are some individual differences that we have to realize in people when it comes to taste and smell. All right. Um, when it comes to taste buds, some people have 3 times as many taste buds as others. And so their sensitivity to taste is greater, and they have stronger food likes and dislikes. And then sometimes people have differences in their genes for their, smelling or olfactory receptors, where certain odors seem to be stronger. So think about if, you have a real strong aversion to a certain odor, but someone else doesn't. That's what these genes. Your genes actually have an effect on. Okay. A couple of generic kinds of things to remember is women tend to be more sensitive to smells than men are. Young people tend to be more sensitive to smells than older people. Okay. And an interesting piece here is that one of the first symptoms of Alzheimer's or Parkinson's disease is a sharp deterioration of olfaction or smells. Okay. So people who are in early stages of Alzheimer's or Parkinson's have this, sharp deterioration of their smells. Okay. There's another condition called synesthesia, which is where a condition that has a stimulus of one type, such as a sound, which elicits another experience, such as color. Let me take that definition and break it down. Okay. The most common type is where you perceive a letter or a number as a color. Okay, so in the text they give you an example of something called this synesthesia, where there's a group of fives in rows and columns, and there's a couple of twos interspersed throughout them. Um, those who have synesthesia can quickly find those twos, um, even if they're different. They're not even a different color when they see them as a different color, even though they're really not. They're all the same color, and they're just interspersed among the fives. They find these twos very quickly. People who have synesthesia, it sort of is kind of a mystery. We don't know that much about it, except that it develops gradually during childhood. It runs in families. So usually if one person has it in the family, synesthesia, then others will have it in the family. And it also tends to run in families of people that have absolute pitch. Remember what we talked about, pitch being high and low frequency sounds when we talked about hearing? Well, families who tend to have absolute pitch also tend to have synesthesia. That's just a little interesting but kind of odd fact. Okay. The next module in the chapter has to do with how should we interpret, um, you know, these sensory things that we feel, how it gets interpreted, how we can, get a signal as to what we're detecting, all that kind of thing. Okay, so let's talk about the slide. This particular diagram shows the probability of someone saying they've think about when you go to the hearing, you get a hearing test, and you have to raise your right and your left hand. So this diagram kind of just basically shows if there's no sound, you tend to not raise your hand, right? Because you're not going to report something that is a stimulus when it's not there. Okay, so you don't hear anything, you don't raise either hand. If it's weak, we tend to usually detect it, but not all the time. That's why it's at 50%. And of course, the stronger it is as you get to the top here, the moderately strong stimulus is when 100% of the time most people will report hearing whatever sound was given in the right ear or the left ear. Okay, so the stronger the stimulus, the better chance someone detects it. Okay, the next slide kind of describes this particular chart where it talks about what's the minimum intensity that you could hear something, okay? And it says that when people are trying to detect some very slight, let's say, stimuli, they they can be correct in two ways, okay? They can say, "Oh, I hear something," and it was actually there. Or they could say, "I don't hear anything." And that's true because it wasn't there. So they're correct whichever way they report those two. Okay. They can also be wrong, though, in two ways. They could say, I didn't hear anything, yet there was an actual sound, for example. Okay. Or they could say, oh boy, I hear something in my right ear, but nothing, there was no stimulus there. Nothing was really being, no sound was being put in that hearing test in the right ear. So you got to think of it that way. So there's two ways that they could be correct, two ways they could be wrong. And then we have something called the signal detection theory. What that means is how good are we at being correct or incorrect with what we hear? So the signal detection theory kind of says, okay, sometimes people say I hear it, but it's really not there. Sometimes they, detect something, and if it doesn't occur again, they're more likely to overlook it, or it's weak versus strong. Do we actually hear it? That kind of thing. Think of when you go to take that hearing test. There's you either report it or you don't. It's either there or it isn't. That's what we kind of need to remember here. Okay. The chapter gets into some interesting information about subliminal perception. Subliminal things are kind of like these hidden messages where we don't consciously hear something, but it kind of, people think it's in like a song, right? Where it's a stimulus that's so faint or brief that we really aren't aware of it, but it's getting into our brain somehow subliminally. Okay, so a good example is to think of if we have a message flashed on a screen quickly, or in a song, we can't really, it's not been proven that it can get into our conscious thoughts and then impact our behavior. um, we're only going to react to it because we had an expectation that someone said, oh, there's a hidden message in that song. Okay, but you can't consciously hear the message. um, so it may not exist. We can't really prove that, so we need to really kind of think about it. All right. Then we have this feature detector approach, where how do we actually recognize objects and patterns? This part of the chapter is really interesting, and I probably will spend some time on it in class, because it talks about kind of these specialized neurons that are in the visual cortex that kind of respond to specific things like lines and angles. Let me give you an example. If we look at something and then we break it into parts, we will detect kind of specific features about it, such as, let's say, the letter of an alphabet. If we look at the letter of an alphabet, one of the neurons that is in our visual cortex will kind of detect any horizontal lines. And then another neuron in our visual cortex will detect a vertical line. And that's what helps us to see that that's a letter, such as the letter H. Okay, horizontal and vertical lines. Okay, different neurons kind of detect those features of horizontal and vertical. There's another great example in the book about a waterfall illusion, which we stare at a waterfall for a minute or two, and then we turn our eyes to a nearby cliff, and the cliff appears to flow upward, not downward. Okay, because the neurons, and we talked about this earlier in the vision section, they get really tired out by looking at the waterfall flowing downward. And so as a result, because those neurons were tired out, they started seeing an upward flow instead because they were kind of tired out. Okay. So there's a couple of interesting things about the feature detector approach. Then we have something called, I'm going to skip this for 1 second and go back. It's called Gestalt psychology. And Gestalt psychology kind of talks about, it's a field that emphasizes our perception of overall patterns. So Gestalt is a German word that means pattern or configuration, okay? And the feature detectors that we just talked about are not enough to really explain perception because they only represent what we call a bottom up. Bottom up means we take parts of something, we combine them together to form a whole. So we can see something in a whole something, okay? However, perception also has to include a top down, means we take our experiences in the world and our expectations for what we think we're seeing and we interpret it. Okay, so I want to go back to this particular figure. Okay, because if we look at the item on A, letter A, many of you probably saw it as the cat in a hat. Okay, and it's based on the context because are we seeing this as the letter A, or are we seeing it as an H that's kind of just got crooked lines? Um, and we're seeing them as A's because we know from experience the phrase. We look at the context of it, and we all know the Cat in the Hat as a book that we may have grown up with. Okay. In addition, look at this one in B. If you read it top to bottom, you may see 12, 13, 14, but if you read it left from right, you'll see A, B, C. Okay. So again, if we see this middle part as a B or a 13, it really depends on if we're reading the slide side to side or up and down. Okay, that has to do with, again, how we're seeing things and part of Gestalt psychology. Okay, there's a couple of other kinds of principles here that I'm probably going to talk about in class. Letter A has to do with proximity, and this particular one in A, we perceive the objects that are close together as one whole group, even though they're different. B, we perceive these items as, how we group them. We see all the X's first, or we see all the O's first as two separate groups because they're similar in how they look. Okay. C is called continuation, where, okay, we see the end of a hot dog here and on this side, and then we see this green rectangular box, and we almost have to assume that the box is over there, but the hot dog continues from this side to this side. It's just behind the green, okay? Even though it's covered by the green rectangle. D is what we call closure, is that we have a familiar figure, whether it's the apple or I believe this is President Lincoln, or a photo of a person of some sort. It's a familiar figure that's kind of interrupted, but we're able to kind of close what we think the rest of it is to see something more simple, okay? And then for E, we are drawn to really good, regular, symmetrical kinds of objects here. Like here we see red on top of green, but we can say to ourselves, okay, I see a red square and then I see a green square. Sometimes we may see this as a backwards L, the green, and it's kind of up against the red, and then this other piece somehow appears in our vision. It really does depend, okay? There are lots of similarities between vision and hearing. So we have to keep in mind that when we're talking about Gestalt psychology, besides vision, it also has to do with hearing. Think of a clock. A clock can sound the same in a variety of ways, though. It can sound tick tock, or it can sound like tock, tick. It's kind of how you're perceiving that, okay? We also have those principles of continuation and closure that we just saw here, where we see objects continue to move even if something is blocking them, or we hear gaps in a song if they're filled with some sort of noise in between those gaps. It's where one item kind of interrupts the other, okay? So that's C And D, when we talk about continuation and closure, we have an item and some other item is interrupting it. But we often apply our experience and what we already know to fill in gaps. Okay. We also need to perceive movement of things and depth. Okay. So when we're looking at objects, they're going to keep their shape, size, and color despite their distortions in how they're actually reaching our retina for us to see them. So here's an example. Um, if we are looking at a picture of a door, or we're looking or standing in front of a door, if it's closed, or it's, let's say, half open, or it's fully open, it's still a rectangle. So we tend to perceive that object still as a door, no matter if it's open, closed, half open, because it's a rectangle. And that's one of this idea of visual constancy. Okay. um, Despite how it looks, half open, fully open, we still tend to use our perception to decide, okay, well, I know that it's still a rectangle. Okay. In addition, we perceive an object as moving if it's moving in relationship to the background. We look at the background, see the object, it's in a background, and we kind of perceive it as moving, and we look at the background to see if the background is stable. Okay. We can also distinguish between an object that's actually moving and, a kind of way that our retina is being stimulated based on our own movement. So let me explain that in terms. Our brain can interpret the difference between an object that's moving and your eyes that are moving. It's often because the background is changing. And that's what our brain will also look at as well when we're talking about perception of movement. All right. And then we have this perception of depth, how deep something is. In a 3D way. So you might want to put next to depth perception 3D, because perception of depth depends on several factors. All right. These two things called retinal disparity and convergence. Let's talk about each one first. Retinal disparity is where um, you can look at an object, and if you close the right eye and look at it and then close the left eye and look at it, you will see it in two different ways. So for example, if you put your finger in front of your eyes, if you close your right eye, you still see that finger, but if you switch and close your left eye, it almost looks like your finger moves in a way. Okay. Because the left and right retinas are actually kind of focusing in on it in a different way. All right. Convergence is the degree to which our eyes turn into focus. So if you take your hand and hold it very close to your face, your eye muscles will actually start to hurt because they're kind of converging, meaning coming together, and the eye muscles are really pulling in to look at that hand. Okay, and it actually will hurt if it's very, very close to your face. As you move an object closer to your face in front of you, your eye muscles feel very they strain a bit, okay, versus if you shift your hand further away from your face. We're going to try that activity in class, all right? And then retinal disparity and convergence are called binocular cues. Binocular has to do with two eyes. So if you want to think of looking through binoculars, or BI stands for two, these are cues that depend on both your eyes seeing them. Okay, whereas monocular, or mono, if you want to circle mono, refers to one eye. The visual cues to distance are just effective with the one eye. Um, just as looking at something, you'll be able to see it distance wise as good with one eye as with both eyes. Okay, so there's a two different ways to look at that. Okay, this last slide really gives kind of what we call optical illusions. The last or end part of the chapter deals with optical illusions, and optical illusions are a misinterpretation of a visual stimulus, meaning, so something that we are seeing that's stimulating our brain to say, hey, I think that's this, or I think that's this. It's a misinterpretation of it, okay, for a variety of reasons. And it's often the result of misjudging some sort of distance from our eyes to the object that we're trying to see. Okay, so if you want to take a look at these in your own time, you can actually answer some of the questions and they give you the answers at the bottom. But we might take a look at these in class, that you could see optical illusions. They're always fun to look at. Okay, so there was a lot in this chapter, but again, if you read through the chapter, and listen to the PowerPoint again, we will discuss in class and do a couple of activities with it. It will come easier. So just keep in mind, we're dealing with sensation and perception, sensations, and how our experiences kind of help with that. There are things that happen in both the eyes and the ears with their structures, the taste buds, okay, and the cutaneous senses of touch that impact how we experience certain things and how it varies from one person to another. Okay, so that's the main idea of the chapter. So if you want to think of it that way, that would be great. Okay, I'll see everyone in class.